The gentleman in the sport coat in the back and the lady next to him aren't from Homeland Security. That's actually Dave Newcomer, who is the NGS Geodetic Advisor to Florida, who has the only stable benchmark in North America. And the lady, of course, is my wife. So please say hello to her when you get a chance. Her name's Gail. There's kind of a situation. I'm going to be speaking to you as a geodetic surveyor today. My roots are in surveying. I'm a land surveyor by profession. And there's good news and there's bad news. The good news is if you can wait 8 years, you're home free. The bad news is we've got to do something in the next 8 years to get our heights. If you live or you work anywhere from the mid-latitude of Louisiana, frankly, you can't trust anything in the ground down there. That's my own personal point of view. Thank goodness, as Dr. Vassaraj said, for C for G and the real-time network. Tim Osborne so eloquently told us about the rather dire condition in Louisiana. Thank goodness for C for G. And C for G, as we talk today, you'll notice that I'm going to suggest C for G as a source of orthometric height truth. I think that might be a 8-year solution until we get to the new data. Dr. Joshua Ken, his work, I was talking to him during the break, he's actually working toward that end with gravity and orthometric heights. Need to thank C for G for inviting me here. This is actually our 4th time down here. We love it down here. We're happy to be here. I'm honored to be here, so I appreciate you sitting in. I think we have a lot to cover today. I'd like to suggest that if there's something important, this is a large room, so if there's something you'd like to ask or contribute, we can do that. However, we do have a panel session that we're going to do after the last break. So that might be a good time maybe to ask a question to the panel, maybe make a note or something. That might be my suggestion. So today, the rest of the day, until the panel session, this is the plan. We don't have to stick to it. I've got a ton of material, and I've got things that I've been researching for months in Louisiana, and I'm sure there'll be some things that won't get said. I think the first thing we want to do is look at the situation here. I have the first set of slides. We're going to try to get a concept of what we're dealing with for orthometric heights. Then we'll get into some background information about geoids and heights and dynamic heights, things like that. We're going to end up with guidelines for static static positioning, and the guidelines for real-time positioning, best field methods. I hope to get to the static guidelines right before lunch, if we can do that. Okay, there it is. Very simple concept. NAVD 88 orthometric height. All you need is an ellipsoid height. Okay, that's great, because we can go out and get really good ellipsoid heights. C for G, RTN, real-time network, has ellipsoid heights du jour. They know where the antenna reference point is every second. So we have really good ellipsoid heights. That's great. So all we need to do is get this geoid model between the ellipsoid and the datum surface, NAVD88 surface. We're home free. We got an orthometric height in NAVD88. We probably all know that it's not that easy. NAVD88 is based on, it's realized by marks in the ground. There's problems with marks in the ground here. The geoid model has error. It's built on gravity. The terrestrial gravity information, fortunately, has been smoothed out by the aerogravity in the GravD flights, but it still needs to be updated and densified. So we've got a problem here. We've got a very simple equation, and we've got trouble realizing it. Let's look at our tool. Cliff gave a really nice talk, an interesting talk on the background. As we can see, we need the military and politicians for what we have, right? So our GPS constellation is part of this. Maybe 32 satellites up there that are usable. Department of Defense. GLONASS is the Russian Aerospace Defense Forces. Maybe 24 satellites. Galileo plans to have 30 satellites from the European Union, European Space Agency. And of course, China, you can get that from Walmart. No, actually the Chinese National Administration, Space Administration. So, in about 10, 15 years, we'll be able to walk around and get positioning like this. Probably better than that. Half a foot or better. How about vertically? Well, by then, we'll have the new vertical datum, and we're home free. So this is what we have to worry about. We have to worry about monitoring those marks in the ground, because that's the basis for NAVD 88. There are marks in the ground. We have to see, where are they moving? Are they subsiding? I think we'll see that they're not subsiding at a linear rate. What about GPS on benchmarks? Well, that's great, because if you get GPS on benchmarks, then you have the ellipsoid height, you have a published orthometric height, that you can build a geoid. That's just the difference in that equation. Well, the trouble is, it doesn't cover Louisiana like it should, benchmarks. Plus, after you, I'm sorry about the feedback, plus after you perform GPS on a benchmark and you leave, that's the last thing you know about it. The good thing is, every real-time network station, you know where that ellipsoid is every day. And you'll see, as we get into the presentation, that the ellipsoid heights vary daily. Some of them a lot to worry about. But you can tweak the position. Actually, C4G could tweak the orthometric height of each RTN station based on the ellipsoid height change. So what is stable? What is the source of NAVD 88 truth in Louisiana? It's tough. It's very tough. And then what do we do about the stuff we did in the past? I can show you that the NGS approach is a particular kind of extrapolation of leveling that wasn't done in Louisiana. So the trouble is, if you're basing it on leveling done 8 years ago, how accurate or precise is that leveling? Even if you just use the observations. So the good thing is, it's recognized in Louisiana that to be aligned to the National Spatial Reference System, which is the system of coordinates of the United States, the national datums, it shall be specifically based on the public domain, Louisiana State University Continuously Operating Reference Stations Network, and other NGS and NOAA products. So it's in the annotated code that C4G, GolfNet, is the source of truth in Louisiana. And I think this is where we have to base our truth. VTP, vertical time-dependent positioning, it looks, well, let me just say right now, it's based on leveling done in 2006 and 2004 in Louisiana. There's a graphic here that I'll bring up showing the most recent leveling in Mississippi. And what they simply did was they looked at the change over time in that leveling and projected a trend that they applied from the leveling that stopped at the Mississippi border, extrapolated new heights for the benchmarks in Louisiana. The trouble is, I don't think that extrapolation is as accurate as we need, but I will say that the NGS has labored mightily in this area. Over the years, over the decades, they've put a lot of effort and time into this. The simple answer is we just need more data, more gravity, more elevations. But the approach has to be correct, because anytime we go out and level, it's only good as we walk away from that point. And we know that the subsidence is too great in Louisiana to trust an orthometric height that was leveled over time. Can't do it. So these are other things we can look at as far as monitoring subsidence. Interferometric synthetic aperture radar can give you about 1 centimeter. That's pretty good. That's pretty good. We can see pretty good change that way. So that's a really valuable tool. It can be done either by satellite or by airplane. And these other ways, some of them are practical, some of them aren't. HTMOD campaigns, where you do a GPS network across the state. Again, you're talking about an accuracy of 2 to 5 centimeters. And then once you do it, you're dealing with the same thing again. You have no concept of what's going to happen next year. How much has that mark moved? It's a problem. Some of the reasons Dr. Roy Daca has pointed out. But you have plate subduction, where the plate is diving under another plate. You have low-lying areas like swamps that are being compacted by use and infrastructure. Obviously, fluid withdrawal, maybe sinkholes, things like that. It really doesn't matter what the reason is. You and I don't have godlike powers to stop it. It's just, as Tim Osborne said, how do we approach it? How much money do we spend? Our job is to monitor it as accurately as we can, measure it as accurately as we can to get proper orthometric heights as surveyors and engineers. Now, I brought this slide up just to show you what the concept of subsidence was. This was actually to dealt with the new adjustment of NAVD 83 2011. But this was considered a 10 millimeter a year area. This was considered a 5 millimeter a year area. This was I believe a 1 millimeter a year area, and this whole outline here was a 3 millimeter a year area. So just to show you the NGS approach toward subsidence. This is interferometric synthetic aperture radar shot, just showing the spectra involved that can be monitored for change. A couple shots over time, you can develop a topography. This is a very valuable tool to monitor subsidence. Here's the simple static shot of the C4G network. I would submit to you that if we can put orthometric heights on these guys that we can trust to a couple centimeters, if we can do that, then we label them as truth. Now, why do we want to do that and not something else? Well, we know where those antennas in the air are every minute, every second. The change in antenna height by ellipsoid height monitoring is a change in orthometric height at that station. So, as that station subsides, and you're saying, well, they're pretty stable, they're not going to subside. Well, Dr. Roy Daca and Chris Schinkel in Mississippi said, yeah, they do. Core stations agreed within a couple millimeters a year of the subsidence on the other stations. So we're saying, okay, well then maybe we can monitor subsidence with C4G. I think we can. And what I'm saying is we're going to label those stations as orthometric truth. Can't do it yet. We could, but we don't know the accuracy of what we do. The accuracy of those antenna reference points has to be done again, and I'm going to say with a different geoid model. But it has to be done again and updated. Once we can get orthometric heights on those antenna reference points, we're going to call them truth. That truth then can be monitored, not like the marks in the ground when you walk away. You don't know what happens to that mark. And believe me, it's not just a subsiding, it's going like this. So it depends when you hit that mark again, what it's going to look like. That's why I'm a little bit hesitant about the extrapolation of VDP across Louisiana. somehow they would develop a trend based on 2006, 2004 leveling. You know, I mean, and I'm sure it's as good as can be done. But maybe this is a better answer. Rely on the C4G RTN stations. Rely on their orthometric heights. Okay, they're 2 centimeters. If they're truth, they're truth. Something has to be true. You have to base your work on something. Why not base it on something you know how it changes? Here's a English turn, actually 2. But you can see that this station is subsiding, I don't know, 4 or 5 millimeters a year. It actually got beyond what the NGS cutoff is, like 4 centimeters ellipsoid height. They said, well, when it gets to that point, we're going to reevaluate it and see if we really need to change that height. Well, it got beyond that, but eventually I think it was changed. But this is just to show you that a core station can monitor subsidence. Here's another thing. This is a short-term plot. Let's call it 90 days. This is the north, the east, and the up being the ellipsoid height. North, I don't know. To me, that looks like a little bit of a bias there to me. A centimeter. East, that looks okay. And the up. Now look at this up. Suppose you were at this day ellipsoid height and this day. That difference is, I don't know, 3 or 4 centimeters. Just the height varied from day to day according to this adjustment, 3 or 4 centimeters. Here's this one, this one. Now, was that the adjustment? Did it really change that much? Who knows? But we do know that it changed in this adjustment. Therefore, if the C4G can do the same thing, and they certainly can, give a short-term plot, why can't they do elevations du jour? You know, have elevations that, if it changes beyond a certain parameter, say a centimeter or 2, actually say today's elevation of this station is, or build it right into the interpolation for the rover within the network. Trying to find a source of truth that it's precise and accurate. Tough. But maybe this is an answer to monitor the RTN stations. Now this is a long-term plot and it didn't come out very well, did it? But this is 2004, 2010, 2012, I believe. And you can't really see it too well, but it kind of goes almost like a sine wave. It goes up and down, like centimeters up and down over time. So again, there's no linear component to that. It may be almost cyclical, maybe, but it is not linear as far as being consistently down or up, right? So how do we know what's correct to use? Well, again, go back to the short-term plot and look at it. So can you see that we're trying to pare this down so that we're dealing with maybe a couple centimeters to our site? If we can get good ellipsoid heights at our site to a centimeter, and if we can nail these down so that we know that the orthometric height is accurate to a centimeter or 2, then we're starting out aligned to the national vertical datum a couple of centimeters, 2-3 centimeters, 9/100 of a foot. That's not so bad. Now, then you can use your precision at your site to densify as you need. But at least it ties everything together. Josh will be very happy about that in his GIS. Okay, another one. You can see this one a little bit better. You can see how it varies up and down over time. 2008, 10, and 12. And here's the published. And you can see that the published velocity upwards is a little under 4 millimeters a year. But if you use that and said it subsided 4 millimeters a year, you'd be wrong, because it didn't, did it? Same thing. Here's another one. This is LWES. You can see how this ellipsoid height is changing. And if you had to fit a line through there, best fit through there, I'd say there's a bias as well. Wouldn't you? A couple centimeters maybe? So every day it's wrong by 2 centimeters, according to the published value, which is the 0 line. These guys look great, north and east. But we're not really caring about that, are we? We care about the up component. I'm just saying it varies too much to rely on, unless you can look at something like this and see where it was in the day of your survey. This brings up another problem. When you use a real-time network, you're using the published value of that station, which includes ellipsoid height. When that station does a network adjustment within itself of a cell of stations around where you are with your rover, it's going to use that value. Now, if that value is off 2 or 3 centimeters, it's holding those values and saying, well, we got to figure out what's going on here. What's going on with the ionosphere and the weather, the troposphere, and let's see, the orbits and stuff. Okay, we know these coordinates are right. Well, they weren't. Not by much, but they're not right. So that has to go somewhere. So what happens? It gets slopped into that atmospheric modeling. Okay? Then it's sent to the rover. We know how a VRS, a virtual reference station network, works. It creates a pretend station by you, and it sends the information as if your base station was right there. So you have no error as far as interpolation. The interpolation was done to that virtual base station. So your base station's wrong. Not by much. But then you're adding the error in the geoid, the error of your ellipsoid height, the error of any mark on site, of course. So we want to keep down the cumulative error. Why not start as well as you can? All right? So I'm just saying, that's a problem with antenna published values. We just saw that they go up and down, they change. But you have the ability to do that daily. Okay, you don't publish it at the end of the day. Maybe you have a day delay or 2 days delay. But then you can still tweak it. Velocities. The NGS does not have vertical velocities on points. They're working on it. But as you can see, to my way of thinking, if you don't mind me saying, I think it's a waste of time right now. I don't think you can produce an accurate vertical velocity on points in southern Louisiana. I'm sorry, it's just my personal point of view. And I'm not saying I'm an expert. I'm just saying as a geodetic surveyor of 45 years, this is what I would say. And we already said that it's not regular. The movement is not a regular movement. All right, so 2 kinds of geoids. One's gravimetric. That just means an equipotential gravity surface. Gravity is the same, right? Water will not flow on that surface unless acted on. And a hybrid. Well, why the heck do we want a hybrid? Let's just use a gravimetric one water is level on. Well, because our datums don't work that way. First of all, NAVD, let's see what we got slide-wise. Of course, any equipotential gravity surface, if you will, equal gravitational acceleration, okay? Meters per second squared. You can have an infinite number. We're going to pick one out. And we're going to say that fits global mean sea level in a least squares adjustment sense. All right? And that's what we call the geoid. Equipotential gravity surface that fits global mean sea level. Wonderful. It's not what we use for NAD 83, though, or NAVD 88. So the gravimetric Dave Doyle says everyone should have this tattooed on their left arm. You have it right here. Equal potential surface of the Earth's gravitational field, which best fits in least square sense, global mean sea level. The hybrid is a conversion surface that will work with NAD 83 and NAVD 88. Neither one has the same datum surface. So you have an ellipsoid height, you have the orthometric height truth based on something, and then you have the model as a separation between the two. I think we were pretty jake with that. NGS gravity holdings. The trouble is, there's good news and bad news. Bad news is terrestrial gravity over the last 60 years has very poor metadata, data about how they did it, and you know the precision of the gravity readings, all on paper. And maybe not as accurate as we like. The good news is because of GravD, they have flown the Gulf Coast with aerogravity from a plane, absolute gravimeter. And they have really good information now that tied things in. They can smooth those terrestrial readings out with that aerogravity. And they've developed a beta geoid model. And I think that's what we should use in Louisiana. The other trouble was, with all these ship gravity readings out here, they couldn't get that close to shore, right? So you had this gap between the coast and where the ship gravity readings were. That was taken care of with GravD when they flew. So that's good. It tied in the ship with the shore, smoothed it out, created a nice gravity surface. This is a good thing. So you have a gravity field, starting with the satellites, the Earth gravity model, 08, you know, but kind of long wavelengths, you know, but nice smooth surface that gives you the nice pretty picture of the Earth. Then you move down to intermediate with the airplanes and ships and things like that. Then you move to terrestrial gravity. That gives you the precision along the ground. You put all that together for a nice gravity model. Here's the gravity recovery and climate experiment model from these satellites 500 kilometers up there. They're still up there, functioning. This guy crashed and burned, Goche, but he did good things when he was up there until 2013. Long wavelength stuff. GravD now is funded. It's going to provide us with a new vertical datum, new basis for a gravity model. The good thing, like I said, is they've done the Gulf Coast. Very good. Always this dichotomy, always. Marks in the ground that we've trusted over the years, but we don't know where the heck they are, really, up and down, and antennas in the air. Antennas in the air are the basis from the core system of NAD83, our three-dimensional geometric datum, lat long ellipsoid height. NAVD88, based on marks in the ground. And that's the realization of that datum. There's errors in both, of course, but the biggest error we deal with, I say we, people in Louisiana, engineers, surveyors, and others, deal with heights. As Tim Osborne said, it's critical because we know what a small change in height can mean as far as where that water goes. Same kind of problems in Maryland, Delaware, but not, of course, to this extent. Chesapeake Bay is subsiding also, but only maybe a couple millimeters a year. NAVD88, based on one benchmark, as most of you know, Father Point Rimulski, or Pointe-au-Père, in the St. Louis Seaway, for a number of reasons, to tie into the International Great Lakes datum so that they were homogeneous, not to change the charts and maps too much, and then to use leveling across the country. Really good, really, really well done. However, even at 0.5 millimeter, a mile, it still adds up to over a meter when you get into Washington. So there's a tilt. against true gravity, true equipotential gravity, NAVD is tilted. Also, it's biased. It's not at the same datum surface as global geoid. It's about a half a meter above it. So you've got a bias, you've got a tilt, and of course, to complicate it further, you've got ellipsoid heights that aren't from the same geocenter. You've got a situation like this. Yes, it says 86 to 97. It's okay, it's still the same. And the difference is a nice smooth difference going across the country between NAD 83 ellipsoid heights and IGS or ITRS systems of their ellipsoid heights. They're based on a true geocenter. And NAD 83 was the first global datum. And they did a great job with it. It was done before GPS. Of course, GPS came out immediately after they released it, and everybody said, hey, I got a meter. Okay. But it was all, they missed geocenter by a couple meters. Pretty good. But because it's biased, you have that problem with the ellipsoid heights. So to go from a geocentered datum to a non-geocentered datum, that has to be taken into account. Well, a geodetic datum, you need a surface, which in this case is an oblate spheroid, squashed a little bit, and based on a certain parameters of semi-major, semi-minor, flattening and all that, best fit to the Earth, right? Okay, great. Well, it has an orientation, semi-major axis, X, Z, 90 degrees to it, right-hand coordinate system, Y out through the equator. So you define your parameters as a prime meridian, an equator, and a surface. And where you put that is the difference in the datums. NAD83, here's NAD83 ellipsoid, here's the IGS or ITRS ellipsoid. Same size, same ellipsoid, GRS80, just starts at a different origin. That's why you have that bias. So you can see you can have an XYZ, and indeed, the satellite system, GPS, is all XYZ. Any point above, below, or on the Earth can be defined in XYZ, right? Based on this system. On a certain datum, whatever datum. So you know XYZ, you get XYZ, but you can also define, of course, longitude, latitude, and now a height component, ellipsoid height. So now, with GPS, you have a height component, ellipsoid heights. It'd be great if that was also an orthometric height. However, it isn't. This is showing the bias between the origin of 83 and, let's just say, ITRF. Couple meters, and that's why you have a different ellipsoid height. Fit to the Earth, semi-major, semi-minor. Now, the GPS system is based on WGS84. It's actually a little bit different ellipsoid, WGS84 ellipsoid, but only to the 6th decimal place of flattening, so it's the same. We're talking about a half a millimeter from Alaska to Florida or something different. So, and we talked about, let's go past this. The key to a hybrid geoid model is GPS on benchmarks, as we said. You got the benchmark, so you got a published value, NAVD88. You got your ellipsoid height. The only thing left is a geoid separation. So you got that if you got the other two. That's why Dan Roman would love to have more GPS on benchmarks so he can create a better model. So, conversion from gravimetric geoid to the hybrid geoid, which we use with NAD83, we said what's happening. The tilt, the bias, the transformation of the ellipsoid heights. All that is built into GEOID 12A, which we use now. The other previous hybrid geoids and the new beta geoid, XGEOID, scratch that. XGEOID 14B is the one we want to use as based on a gravimetric geoid, not a hybrid geoid. There's our formula again. And just to show you, this is a published orthometric height to the nearest centimeter or nearest tenth of a foot. 209.55, and it says leveling. When you see leveling, that means that has used VTDP extrapolated from previous leveling information to come up with an orthometric height. That's why it's only published to the nearest centimeter. You know, it could be right on the money, or it might not. The thing that I look at is what gives me confidence with what I'm doing. And to me, I want to use something I know, like C for G. And this will say it used VTDP, and it's in a known vertical motion. Only use it for the epoch that it's published. And the epoch is 2009.55, mid-year 2009. Well, that's great. It's mid-year 2014. That means they're just telling me that I can't use that. Are we going to use it? Probably. Superseded control. You can look at that and see how things have changed. Here's a summary of it. Ellipsoid heights vary. Now, another thing to understand here, ellipsoid heights will vary anyway with a new geoid model. You have to use the right ellipsoid height with the right geoid model. Okay, so NAD 2011, you're going to use GEOID 12A. If you use HARN information, or say NAD 2007, or CORS 96, you're going to use GEOID 09. Okay, so your geoid will change with your ellipsoid height epoch. Understand that. Anyway, published and GPS-derived. So, I mean, this is only, you know, it's very close. This is not too good. This is a couple centimeters. It's not how much it's different, it's how much can we trust it. Some reasons for whether verticals are harder. First of all, if you think about a horizontal position from satellites, your coverage is almost 360. Not quite, because there's GPS, as far as GPS goes, there's nothing, maybe 35 degrees either way in north. So you've really only got, you know, 290 degrees or something. But you've got a field of coverage where you take the vertical, and if you've got a 15-degree cutoff angle, you've only got 150-degree coverage. So you have less coverage vertically than you do horizontally. Anything that affects the signal coming down seems to affect the antenna phase center or the vertical part of the solution more than the horizontal. Also, when you're doing real-time work, you're using broadcast orbits. What does that mean? It just means you're using what the satellite is telling you where it is. That's not true, of course. So you don't really know where it was until 10 to 14 days later, but there's something called rapid orbits that are much better than they used to be, and you can actually use them to tweak your answer. But right in the field, as you're getting positions, you're using a broadcast orbit. Okay, so there's source of error for verticals. And of course, when you use this magic formula, all those components have errors in them anyway. Ellipsoid heights, geoid separation, the published values on your marks, all of them have errors, and they're going to accumulate. Verticals are harder than horizontal. We'll see that when you use the NGS guidelines for static positioning, GPS-derived, and it is GPS because they haven't got any guidelines for GNSS yet. When you use those guidelines, horizontal is a given. If you can get the vertical to come out, the horizontal is a given. So here's the theory with GPS-derived or GNSS-derived heights. They're saying we can do the ellipsoid heights to 1.5 centimeters. The geoid separation, 0.5 centimeter and 10 kilometers. I think it's worse than that down here. And then leveling is fixed. So the benchmarks we find in Occupy, we're going to use them as truth. They're published. They're good. Well, that's the theory. And that's why they say you can come out with 2 centimeters for GPS-derived orthometric heights. It's a good procedure. It's a good procedure. It's actually being updated. There's a study going on out of South Carolina. Is this the place? Not yet. Out of South Carolina that you'll see a slide on. Matt Wellslager down there, who's head of the South Carolina Geodetic Survey, has done a survey to hopefully update those guidelines. And I think it went to Ohio State or something like that. So, GEOID 12A, it used NAVD 3, it used VTDP-derived orthometric heights, and it published to 2009.55. If you see that, and it says leveling, you've got a VTDP-derived orthometric height. And this is inside the subsidence region. Outside in Mississippi. So here's the benchmarks that were used. You can see, I don't know if you can make out the state line here, but you can see Mississippi had the leveling campaign, and then you can see the X's are the ones that weren't used. Thanks to Michael Dennis at NGS for this slide and others. There was a presentation in March 2013, about a year and a half ago, on Louisiana heights. And a lot of these slides came from that. I'm trying to summarize, but you can see accuracies here. Where there's benchmarks, the accuracies are better because they're using those values. I should say that the VTDP-derived orthometric heights are validated by height modernization surveys. So they're using a GPS campaign over the benchmarks and validating the ones that were extrapolated using VTDP. But you can see there's some benchmarks here, and there's some areas that 4 to 6 centimeters, 95% confidence, and areas that are yellow, 6 to 8 centimeters, 95% confidence. So, I just think that we can do better temporarily. The leveling was done in Mississippi, 2009-10, and it got to the state line, and that's where it stopped, That's the state funding. And then these benchmarks here were constrained. Interesting. You go to the NGS website, and you pull up this benchmark, and it comes up, and it was leveled in 1994. And there's a published value for it. You go to pull up this benchmark, U20, and they won't let you pull it up. It's in a known area of subsidence. You can't get that. Both of them are labeled first order. How come I can get this one and not that one? I don't know. That's even nearer to this other leveling, so they ought to really have a good handle on that one. These two down here are published as third order. They're done by VTDP. And if you look at the superseded control over the years, I can see why they were constrained. You sort of have to have something down there to hold. So I think they looked at the history of these two marks. I don't mean to speak for them, but it appears that they looked at the history of these marks and decided, well, these two marks we can probably constrain, or at least heavily weight in favor of their values. This is a mark in western Florida in Dave Newcomer's kitchen down there. And that was held. That was a stable mark. Then there was another stable mark in Texas, Lake Houston. Those are the two nearest stable marks. And they did leveling in Mississippi and everything, but they did not do leveling in 2009 and 10 in Louisiana. So we've got at least 8 years between the last time benchmarks have been leveled. And frankly, I think, personally, I don't think it's worth the effort to re-level. A lot of money, a lot of time. I think you can do just as well with the real-time network because you know the change. You know the change. All right, again from Michael Dennis. Appreciate this slide. Basically, NGS has labored mightily. They've done a lot of work and put in a lot of effort along the Gulf Coast region because it's important, of course. Again, the final answer is in 8 years when there's a new datum. You can access that datum with your GPS receiver. We have to work with something between now and 2022. I think I'm really encouraged after hearing Dr. Kent talk about what they plan to do for the network. They plan on getting gravity readings to establish a new quasi-geoid. They plan on getting orthometric heights on the antenna reference point. If they can do that, that will be your truth. That will be your truth for Louisiana for the next 8 years. Am I misspeaking, Josh, or is that about correct? We would hope. Okay, let's leave it at that. And I think I'm really encouraged. I think this will be a good solution. Now, let's see. What time we got? We got 11:15. I get to talk for another 45 minutes, right? Or do we want to take a break? Are we okay? Okay. Can I roll? I've got a lot of stuff. Can we keep rolling? Anybody has to take a break, please. Go ahead. Okay, so he says, extend the leveling. Too much money and time. This is a personal opinion now, okay? Establish GNSS infrastructure to monitor subsides. Well, gee whiz, where are we going to get a GNSS infrastructure? Oh, we got one. Okay. And then new HTMOD surveys across Louisiana. You got a network of stations already that you know where the antenna is every day. Why do a lot of GPS, GNSS work and not have confidence in where that station is 6 months from now? I don't know. This is, again, personal point of view. Medium term, terrestrial gravity surveys. Yes, right at the RTN stations. Establish a new surface that we can base our datum on. Incorporate gravity, aerial gravity into the geoid model. It's been done. Here's the geoid, XGEOID 14B. Good and bad. Bad, it's not used with NAVD 3 ellipsoid heights, although you can get they'll transform it to a GEOID 12A height. Good news, I think it's much more homogeneous and much more accurate than GEOID 12A because it incorporates the gravity data from the flown data. It brings everything together. GEOID 14A, not shown here, I'm sorry. The one before the GEOID 14B did not incorporate the flown data, the GravD data. So 14B, I don't know, just looking at it for the last few months, I think that might be a good answer. Long-term, new vertical data. That'll be the answer, but it's 8 years away at least. I'll explain that. All right, so GPS on benchmarks in the hybrid geoid model 12A. I see a lot of X's, and I don't see a lot of brown circles in Louisiana. Remember, if you got a GPS on a benchmark, if you trust the elevation of the benchmark, then you've got a geoid separation automatically. That's why it's so great to have them. A lot of them in Mississippi. And these are the GPS on benchmarks after the GEOID 12A model. There's a lot more, right? Now, hopefully all these guys went into that XGEOID 14B. So to me, that's a good sign right away. This is what the NGS would like to have in the way of a priority. You can't really see the colors real well, but the highest priority is like a red circle. That's these guys. And so I don't know the story of all them, but they look like they're along a road probably an interstate or something, or either that or a rail line. But they would like to see GPS on these benchmarks to build a better geoid or quasi-geoid. What about this area? Is there anything in that area? I don't know. But if there is, if anybody has to work in that area, you know, it's tough. So, but guess what? There's C4G, GolfNet stations in that area. Okay? You see where I'm going with this? All right, GEOID 14B. There it is. Now this area here is the GravD aerogravity data that was incorporated into this model. Okay? This is the difference between the ones that incorporated it and the ones that didn't incorporate it. And you can't see too well, but you can see these yellow squares here. This will be a better display of it. Am I blocking you, Steve? Is that all right? Okay. Again, this doesn't come up on the screen real well, but this red area here is about 5 to 7 centimeters difference between the two models. That's a lot. And the yellow is, you know, maybe 3 to 5. I'm sorry, the little orange area is 3 to 5, and this could be anywhere from 1/4 to 3 centimeters. That's a big area. But anyway, it'll give you an idea. Then you got minuses, the difference between these two. So simply said, geoid separation goes in the direction from the ellipsoid. So if you go down to the datum from the ellipsoid, it's minus. Okay, so you got a minus value minus a minus value. Okay, so in other words, the first GEOID 14A, consider that a plus. GEOID 14B, consider it a minus. So if you see a minus value, that means GEOID 14B was greater than 14A and conversely. So anyway, blue areas are spotty, but they're, you know, 4 to 6 centimeters difference the other way. So you can see what I'm saying here. This is, I don't see a trend there. You know, I don't see any definitive way of relating one to the other. I don't know. I don't know if anyone else does or not. But to me, I'm going to dump 14A. And frankly, I'm going to dump 12A. I think we ought to be using 14B. We can't use it with NAVD 3 ellipsoid heights, though. But there's a way around that. All right. They're saying, well, yeah, you could use 14B. You could just compare the differences over a level line. And if you got a flat area, but your 12A orthometrics are telling you there's a tilt, maybe you should be using 14B for the differences. Again, we're talking differences, not the absolute values. And I agree with that. They also say you could use it for tidal benchmarks to see about the variation. Possibility. So what I did was I looked at what you can do, and there, I don't know if I passed the link to it or not. Please see me offline if you need that link. But there is a link to where you can input a latitude, longitude, ellipsoid height, and a name if you wish, and it'll give you this. It'll give you 14B, 14A, US gravimetric geoid. The reason that this gravimetric geoid and 14B or A are different is because it's slightly a different surface. The gravimetric geoid has a different geopotential surface than 14B, not by much. And this is what I input for Seattle. This is the ellipsoid height. This was a station somewhere near Seattle. So it comes up with a GEOID 12A orthometric height 68.329. That is actually what you'll get if you use GEOID 12A. So what it did was it changed this GEOID separation to make it work with GEOID 12A. So pay no attention to that man behind the curtain here. And then here's 14B, 67.151. The difference being over a meter, 1.2 meters roughly. So that's the difference between using a gravimetric geoid and the hybrid geoid in the Seattle area. Okay, Baltimore, where I grew up, the difference is 36.4 centimeters. And Baton Rouge, difference is 12.5 centimeters. So this is the values you can get just by typing in lat long ellipsoid height. And I think this will be important because I think that's what we should be doing. Same thing, this is just to demonstrate if you use the GEOID 12A model, it gives you this separation. And you can see that when it does this computation, it's a different separation. So they're just changing this to make it work with this. And you can see they both come out the same, 8.777 or 8. Ah, here it is. So this is the link to use XGEOID 14B. Here's, of course, the C4G network. And what I did was just simply took the difference between 14B and 12A. Okay, now this is the difference between the two models. Okay, they're not supposed to be the same, but this is the difference. It's like the second derivative, you know, is acceleration. It's kind of the same thing. So you got the change or the difference in these two models. And take a look at the difference in these two models. You've got, they're very close here. I mean, this is only a couple millimeters, you know, 1.8 centimeters, 4 centimeters. This is a plus value out here on an island. And then you can almost see a trend, almost. You should really see a nice smooth trend, really, between the two. And I don't see that, okay? 30.2, 34.7, then back down to 25. 25 down here, 8.7. I don't see any real nice trend there. That's why I say, the heck with 12A. Let's use 14B. Well, we got to figure out how to do that because it's not the same thing. It's not a hybrid geoid. I think the way we can do that, one way, probably maybe not the best way. It's just what I was thinking. I don't know. But you could actually go to the C4G, real-time network stations. It has to have an NAVD 88 elevation established on it. Okay, so somehow Randy and others have to do that. And Josh, and they all have to work on that. And Cliff, and Tony, and Noah Money. It has to happen somehow. So you get NAVD 88 orthometric heights on the stations. Then, what do you know? Okay, you've got a value now you want to hold. You want to hold that value as being truth. What else do you know? You have an ellipsoid height always on that station. So when you get that bump going up and down, hey, that changes the elevation that much. Now, I'm not a programmer. I don't know what can be done and what can't be done. But to me, I think you could probably build that into a little interpolation program. So you got a station with a published NAVD 8, well, it won't be published, but it'll be an NAVD 88 elevation, orthometric height. You've got an ellipsoid height that you know to probably millimeters. Practically no error in the ellipsoid height. Then you've got a GEOID 14B model that's going to give you a geoid separation. Not the right one, but it's going to give you a geoid separation. So what if we build a pretend orthometric height? I don't know. Call it temp ortho or something. You use the 14B separation. You use the NAVD 3 ellipsoid height. Come up with a bogus elevation. Take the difference between that. See, we're using the geoid model. Take the difference between that and the published NAVD 88. And it's going to be some kind of value. It might be in this area, I don't know, it might be a couple decimeters or something. I don't know. So then what do we know? Well, we know then if we had an ellipsoid height over here on our site, and we used the 14B model, and we could interpolate the difference from that station to that station, to that station, we can develop an NAVD 88 orthometric height based on an interpolation of those differences. We're using a geoid model that follows gravity. We're using an ellipsoid height that is based on NAD83. But we're doing it in real time. We're not putting it on a mark in the ground. Well, we are putting it on a mark in the ground, but we're establishing it at the same time we're doing it. We're not relying on a published value from 10 years ago or 5 years ago. Now, I don't know how that hits you, but to me, I've been thinking about it, and maybe it's a dumb idea, but to me, it's an idea that maybe needs discussing. Now, can you sort of follow me what I'm saying? I'm using a gravimetric geoid, but I'm using a NAD83 ellipsoid height. I'm taking the difference in that value to the published NAVD 88 on that station. Using that difference at my site, except not exactly that difference, an interpolated difference from the stations around me. The same stations that are creating a cell to give me my VRS station can do the same thing. They can interpolate the differences. Maybe you can send it in an RTCM message or something. I don't know. Again, I'm not a programmer, but it seems to me I would want to try that. That's all. As a geodetic surveyor, that's what I would want to try. Because I'm basing it not on 12A, which I don't like. I'm basing it on the newest. It's a beta model, yes. But it's the newest model available for this area, based on the GravD data. I like that. Because that's what's going to happen in 8 years. It's going to be a gravimetric geoid again. You're going to be able to set your rover up, or your receiver, and you're going to link directly to the National Vertical Datum. As well as you can do it, the National Vertical Datum will bring it to your site to hopefully 1 centimeter. Your ellipsoid height error will be, well, if you're like me, there's absolutely no error. No, I'm just kidding. Then the ellipsoid height error of 1 centimeter. So you brought the national datum to your site to 2 centimeters. National datum. Wouldn't that be a great thing if you could do that? Well, you will be able to do that in 8 years. But maybe what I was just saying would be a way to do that until then. I don't know. But I would want to try it. It's new. This geoid's new. But I think it's a better geoid. So what you're doing is developing a quasi-geoid, if you will. All right. What happened with NAD83 was the latest adjustment. Then when they roll out the new vertical datum in 2022, they could do this right now, by the way, the horizontal. But when they roll that vertical datum out, they'll roll out a new geometric datum too. NAD83 is gone. NAVD 88 is gone. So why? Well, they're going to take that kink out of the geocenter, right? They're going to, whatever time they decide they're going to do this, I mean NGS, they'll take a certain value of IGS, the International GNSS Service, a bunch of scientists across the world, establishing that geocenter. They'll take a certain epoch of that, whatever it may be. It might be epoch 2022.00, I don't know. And they'll move our new datum to be concurrent with that point. Okay, so now we got a new datum. If you move the origin, you've got a new datum. That's why WGS 84 is a new datum every time they adjust it, because they keep moving this origin. Anyway, okay, so then it'll be our new geometric datum, lat long ellipsoid height. They move the geocenter to that point. Here's the question. NAD83 is fixed on the North American plate. So we're all kind of moving like this together, you know. Well, the world doesn't move like that as a whole. Plates move in all different directions, and they take the average movement of those plates to come up with the IGS datums and that sort of thing, the origin, orientation, things like that. What do we do? Well, I figured, okay, well, we don't want the coordinates to change every day, so we'll probably fix it on the North American plate again. Well, it was about a year, a little bit more than that, I was at the NGS, since I've been at the NGS. But at that time, when they sat in the conference room, And I thought, well, yeah, okay, so they have somebody in charge of this, the geometric data. They have somebody in charge of the geopotential data. So I thought, well, okay, they're just going to, fix it on the plate again. And, there's a lot of people in that room that said, oh no, we're going to make it, we're going to have velocities, and everything's going to change. Depends on your epoch and when your survey is. I went, wow, really? So this isn't decided, as far as I know. Dave, have you heard anything to the contrary? Okay. So the decision is, do we fix that to the North American plate again like 983, or do we let it go with a velocity? It will have velocities on the data sheet. It'll tell you how it's moving, how fast it's moving. And, if you work in ITRF or IGS, you have to apply that to your position, and you have an epoch date on your plat. Well, do we want to do that? I mean, it's work security. Nobody else is going to know what the heck we're doing. So, do we do that? Or do we say, no, we're going to fix it on the plate, and the coordinates won't change that much, because it's pretty stable as far as horizontal. That's a decision. And if you have a point of view on that, you need to get a hold of people at the NGS, even legislators, politicians. But you need to get a hold of people and let them know what you think. Maybe as a surveying society or an engineering society, you should really think about that. Because these guys haven't decided this yet, as far as I know. I mean, I don't want my coordinates to be du jour. I mean, they change enough as it is. And the accuracies and precisions involved. I just want to know that the published value is going to be okay for a little while. That's all. So I don't know. Think about it. However, just like the vertical datum, the truth is in the cores network. So that'll be the truth both ways, vertically and horizontally. All right. Well, 29 to 88. 29 was a bunch of 26 tide marks around the country. They thought that would be 0, 0, 0. Of course, it wasn't, because sea level heights vary according to density and constant tides and things. So that didn't work too well. NAVD was based on the one benchmark. And you're seeing the differences here. Here's the 0 difference here. And here's a half a foot here. So, I don't know, 88 to 29, 2 or 3/10 of a foot. Does that sound right? Anybody know? In here? Not that it matters too much, but you still see some 29 datum. Here's a nice pretty picture of the same thing. But to me, this is all 0. It's not true. The thing that I want to point out here is that 29 is below 88 on the east, so that you have higher elevations with 29. On the west coast, 29 is higher than 88, so you have higher 88 values. So it flip-flops. Now, 88, we know the problem with marks in the ground. That's the main thing. They're destroyed. Loader operators can navigate to them in real time now and find them and wipe them out. They're not, it wasn't adopted by Canada. We know there's a tilt in the datum. We know there's a bias in the datum relative to global mean sea level. So there's a lot of good reasons why we don't want a datum based on marks in the ground. Also, for those other obvious reasons, we want a new datum that we can reproduce using the satellites. And, people have said, well, why don't you just re-level, and get this new datum, we just do all these new observations. Well, because it would cost a couple $2 billion, that's why. And, it's so much easier with satellites to begin with. So here's one of the typical problems, now I used that because I picked it up and put it back on top again. It was fine. No, I'm just kidding. We can't access them. There's no recovery ties to them sometimes. Sometimes you need a search party. And Tim Osborne shows this one. And one thing I want to point out on this one, just because the water's down here and the ground's over here, and this mark is sticking up, that doesn't mean that mark is good. It doesn't mean it didn't subside, because it probably did. It just didn't subside as fast as the ground. Okay, so some people trust that because, oh, it's sticking up, so it's all right. Thank goodness. No. And of course, Randy Osborne's basement. Yes, it's... Okay, so the new datum, the new vertical datum, it'll be based on a gravimetric geoid, an equal potential gravity surface. There has been a globally adopted value for that. It probably will be used. I can't remember it offhand, but it's 62 million something meters squared per second squared. We'll explain that. Anyway, it'll be something bringing to your site to 2 centimeters. As we said, 1 centimeter error typical in the geoid, 1 centimeter error in your work. 2 centimeters, the national datum. Then you densify. You densify to the precision you need. Geodetic leveling, whatever you have to do. You know, it's not something where you say, oh, I've got an interceptor shoreline, 0.5%, that's not good enough, I need something better than that. Well, of course you do. But you're tying it to the national datum a couple centimeters, then you do your precision work, whatever you have to do. First of all, you should be using dynamic heights anyway, never mind. But you densify to the accuracy you need, you bring the national datum to your site to a couple centimeters. The marks that are in the ground will be a caveat emptor, or whatever the Latin is for use at your own risk. There'll be secondary access. Okay, so the marks have no first access reliability or accuracy anymore. NGS will not validate them. They will provide a data sharing service, but they will not, testify to their accuracy. There will be a conversion from 88 to the new datum. Again, that's where you have ellipsoid heights in the new datum. So RTN, one good thing about an RTN, when you do a datum change like this, either the geometric datum, from 83, or the vertical datum from 88, if you got an RTN that does that, hey, you're out there surveying in the new datum. You don't have to worry about conversions. They've already done it for you. That's a good thing about a real-time network. Here's the problem with the new datums. You've got a site that you're working on. You've got some benchmarks around it, 20 kilometers apart. Yeah, you wish, right? And some horizontal control. And, you're saying, well, I've got some legacy plans, but I really want to use the new datum here because I trust that more. I trust that it's going to really show me where water will flow, and I know the accuracy or precision of that. So you say, well, okay, that's great, because it's all based on the CORS network. So I'll just take my rover out there, and I'll use the CORS stations. They're the truth. I just go to them and, well, you can't do that in real time because the NGS will not be streaming data from the CORS station. So what do? Well, you go to C4G, right? So that means that the C4G, GolfNet, whatever their spacing is, becomes your truth again. So it's incumbent upon this network at LSU to be aligned to the national datum, because when you're out there with real-time positioning, and I don't know anybody that isn't using it, well, that's not true, of course, but most companies use real-time GNSS positioning. If you want to survey in the new datum, you need to reach out to where you're going to get that information. That'll be the C4G, hopefully. Hopefully Randy will still be here and make all the conversions and everything. So you're going to reach out to your network as the truth of the new datum, because you can't get it in real time from the CORS network. Can you post-process? Sure. You could send into Opus, you can download the CORS data and process it in your software. Sure, you could do that. But most people don't want to do that. I mean, I don't want to do it. If I can go out in real time and it's good enough, that's good with me. So we'll see that it's important to do real time the right way after lunch, but at least you'll know that the real-time network has value in providing you the current new datum when that happens too.